In this lecture we shall be talking about timing driven placement. In the earlier lectures we talked about various timing issues where you do static analysis of a circuit, we identify false paths and so on, so that some timing related constraints can be satisfied, and if there are violations some measures can be taken. Later on we shall see exactly what kind of measures can be taken, that we shall see later when we discuss some physical design or some physical alterations to the layout, such that some of these time budgets can be incorporated or the modifications done. Now, here in this lecture we shall be looking at how we can place the blocks subject to some timing constraints which are given to us. So, this is actually beyond the timing algorithms or the placement algorithms, I mean, that we had discussed earlier, because at that time we did not consider the timing issues. We just looked at the netlist requirement, the sizes of the blocks, position of the pins and so on, and our objective was to minimize the layout size and minimize the interconnection length or cost, some weighted sum of the two. But now a third parameter also comes in, some timing constraints. We need to place the blocks in such a way certain timing constraints are met. Let us see. So, timing driven placement, TDP we refer to in short, they try to optimize circuit delay, not necessarily area and the wire length only. This is done either to satisfy all timing constraints. So, we had seen that some of the timing constraints may be corresponding to false path. So, ultimately the bottom line is we want to achieve the greatest possible clock frequency. That is our final objective. So, for this we need to use static timing analyzer as a tool. So, whatever STA gives you, that will be used to identify critical nets. But again, as I mentioned earlier, you may be required to do some iterations, because when you do static analysis you are starting with some estimates of the interconnections. So, from where do you get the estimates unless you do placement? So, this can go hand in hand actually, this will be an iterative process. Okay. So, the timing driven placement, it aims to minimize, means one or both of these parameters. Of course, it will try to eliminate the timing violation in terms of negative slacks, but there are two ways in which you can measure that. You can either measure in terms of worst negative slack, you find the slack value that has the greatest negative value in terms of magnitude. So, it is the worst value that is there, or you can sum up all the negative slacks and see the total negative value there. So, either one you can use. So, we refer this T to be the set of timing endpoints. Okay. So, this worst negative slack can be defined as the slack for every net or timing endpoints tau, where tau belongs to T, where T is the set of timing endpoints. So, what is the timing endpoints? The places from where the places into which the outputs are going, because whenever you have a combinational circuit, so you either correspond to an output or that output can go to an input of a flip flop. So, these are typically referred to as the timing endpoints, that is up to which we need to consider what has to be done within a clock cycle. Okay, that is what. So, either the primary outputs or the input to the flip flop, that is the worst negative slack, and the total negative slack is that you see that so whatever slack tau is less than 0, just add them up. Okay. These are the two parameters, you can optimize any one of them or both. Now, timing driven placement techniques can be broadly categorized into three types. One is based on nets, That means you look at the nets individually, don't look at the total paths. For every gate output, you say that if there is a fan out, that is a net. For another gate, there is a net. For another gate, there is another net. So you look at one net at a time and try to place that particular gate or module in such a way that that particular net value gets optimized in terms of the timing requirement. But again, what you need to do here is that you need to have some kind of timing budget for every net. So unless you have this, you cannot do this, right? Because someone has to tell you that this net has to have a maximum delay of say 5 units, then only you can check whether it is within 5 or not, right? The second type is path based, where you look at entire path and you try to optimize the timing of the path. And third one may be integrated, you do not look at individually net or path, but integrate the whole problem under a single framework. So net based technique, as I said, you have to do some kind of delay budgeting. You have to just assign some delay values to the nets. So you can assign some kind of upper bounds to the timing or lengths of these individual nets, and you can also do some method for net weighting. So you identify which nets are critical. So the critical nets can be given higher priority or higher weights. So you can do a static timing analysis based on an initial placement, then you try to identify the criticality of the nets, and which of the nets are critical, give them higher weights. So whenever you place them, give priority to the higher weights of the nets, right? In contrast, the path based technique, as I said, they seek to handle the all timing critical paths, that means from input to the outputs. They do not look at individual nets. These are more accurate because we are more interested in the input output requirements, not requirement of the individual nets. But again, the problem we have mentioned earlier is that the number of paths can grow exponentially for many circuits. Okay, so handling individual paths may not be a feasible thing. So both the approaches, either we are using net based or path based, they has to go hand in hand with the placement algorithm. Okay, so there has to be some kind of an incremental implementation, so that you can incrementally modify the placement and immediately get a feedback with respect to timing and other related things, that how you are proceeding. So timing and this placement, these two has to go hand in hand. So just unlike the earlier case, this has to be done first and then this, but again here we see that there is a dilemma. So unless you do placement, you cannot get the wire lengths, and unless you do timing, you cannot get a good placement. So there has to be an iterative step and incremental, they has to go hand in hand together, right? So in contrast, the integrated approaches that we have also considered, the third approach, they use some kind of a mathematical formulation. They formulate some constraints. So in these constraints, the static timing analysis can be inbuilt, some results of STA, and there is some objective function defined which we are trying to optimize. Okay. Now in practice, some industrial design flow which handle large high performance designs, they do not incorporate timing issues during initial placement, because as I said that unless you do placement, you do not get accurate information regarding the delays. Therefore, they do not incorporate timing driven methods during the initial stages, but during subsequent iterations they do that. Okay. So this makes sense, all right, fine. Now coming to the net based techniques, these approaches impose quantitative priorities with respect to net weights, which can indicate how critical a particular net is, or you can give some kind of delay budgets if you can specify some upper bound of the delay. That means you can either say that this net is very critical, this net is not so critical. This is one way of saying, or the other way is that you can give some upper bound, that will, for this net my maximum delay budget is this. So, you will have to fit within that budget. Okay. There are two ways of specifying. Now, in the initial stages, net weights can be more effective because delay budgets are very difficult to estimate during that stage. Okay. So, initially you can just say some weights, some nets are more critical than the others, but during subsequent iterations you can go for delay budgets. Okay. So, once the timing analysis results become more accurate, so only then you can get the delay budget estimates as well. Let us look at some of the existing methods which have been proposed for this net weighting, how they make the estimates. So, a traditional placement tool that we have seen earlier, this optimizes just the total wire length and routability, or whether there is sufficient space for routing. But to account for timing in addition, the tool can also minimize the total weighted wire length, where this weight will be a measure of the criticality. So, every wire length can be assigned a weight. So, higher weight means more critical. Okay. So, if you can assign some weights, and if you can translate this problem of minimizing wire length to a weighted wire length minimization problem, then this net priority can be implicitly taken into account, just to modify the cost function for the placement, right. Now, the way we assign the net weights can be done either statically or dynamically. So, we shall see some of the approaches that have been proposed. Static net weights, they are called static because they are computed a priori before the placement process starts and do not change during the process. And these are basically estimated or calculated based on the slack values that are calculated through static timing analysis. So, the idea is that the more critical the net, that means smaller slack, the weight should be greater. So, there are two ways that have been proposed. One says that you use discrete values of net weights, two values, omega 1 and omega 2. Just give omega 1 if the corresponding slack is positive, give omega 2 if the slack value is negative. So, omega 1 is usually less than omega 2 has a higher weight. Okay. So, if the slack value is negative, you give those nets the higher priority. Or there is another method which proposes that you can have a continuous value. You can calculate W as 1 minus slack divided by T to the power alpha, where T is the longest path delay in the circuit and alpha is some criticality exponent which you can adjust. You can modify the value of alpha, and by that you can also change that how much the variation in slack will impact the value of W. Okay. So, there are some other method also where net weights were based on sensitivity. So, this was the expression which was used. I am not going into much detail here. So, they used some computed value of the slack, and slack target is the target slack, how much slack you want. Alpha is a parameter, beta is also a parameter, and SW slack says, this means that what is the total negative slack sensitivity to the net weight. That means if the net weight changes, how much impact will it have on the TNS value. Similarly, you can have TNS slack and TNS slack. This is for the slack value and this is for the TNS value. So, how much impact a change in net weight will be having on the corresponding slack value. So, these are some methods which have been proposed. And for the dynamic net weighting, they are modified and changed dynamically during placement iterations. Okay. And obviously, this can be more effective because you are changing the weights based on the current scenario, and the old values can become outdated when you make some modifications. So, this is an iterative value So, the slack value at an iteration k can be calculated from the previous iteration value by making some changes based on delta L. Delta L can be the change in the while length that have been taking place between these two iterations, and this will be the impact of the change in while length on the delay, some factor that multiplied by delta L, you subtract this from slack k minus 1, that will be your new slack. So, once you have calculated the slack, then there are ways to calculate Wk. So, some method have been proposed that you select or classify some of the top critical nets. So, if it is among the top one, you assign a variable Vk like this. If otherwise, you assign a lower value, don't use this plus 1, and once you calculate Vk, you can calculate the net weight as the previous iteration net weight multiplied by 1 plus Vk. You just incrementally update it. Okay. So, these are some of the methods which have been used. Now, the integrated approach is interesting. Here the entire process of optimization you are expressing mathematically, and you are using some kind of a solver like linear programming solver, LP solver, to get a solution to the problem. Okay. That what will be the placement such that these constraints are met. Okay. So, let us see that here how this works. So, in the net based methods, you recall the timing requirements are getting mapped to net weights or constraints, while the path based methods directly look at the timing for the paths, but the path based methods are not scalable. The number of paths can grow very quickly. Okay. So, for scalability and good performance, the timing analysis can be captured by a set of constraints and objective function that can be optimized. For example, the one that we present here uses a linear programming formulation. So, how does it work? They actually specify two kinds of constraints. One is called the physical constraints, those are the placement, so where the cells are located, and timing constraints, that concerns the slack values. So, in addition, you can also incorporate some additional constraints, some electrical constraints if you want, but we only talk about these two here, physical and timing. So, the physical constraint, let us see what these are. Given a set of cells V and a set of nets E, we define x v y v to be the center of a cell V. This should be belongs to, sorry, the symbol has not come, small v belongs to capital V. So, what does this mean? Suppose I have a cell, this block I am placing, I call it V. The center point, center of this cell, I call it the coordinate x v and y v, right. V E denotes the set of cells which are connected to net E, and left, right, bottom and top denote the coordinates of the four boundaries of E's bounding box. So, what does this mean? Let us explain. This E denotes a net, right. Suppose this is the bounding box that is represented by E. E denotes a net, means there are some points to be connected, and I am using a slightly larger bounding box with the assumption that all interconnections will be completed by this bounding box. Now, we consider some edges, left, right, top, bottom. So, with respect to this, see, left means some x coordinate, this is left of say E, this is right of E. Left E and right E refers to some x coordinates, and top and bottom refers to some y coordinates, top of E and bottom of E. they refer to some y coordinates. Okay. So, with this we will see that how the constraints are, and the last one, delta x v e and delta y v e denote the pin offsets from the center for V's P connected to E. So, from the center where the pins are located. So, you see, so once we have defined the bounding box, we expect that all pins has to be there. So, from the center we are measuring delta V, delta x as the x and y offsets. Okay. So, they should not be outside this bounding box, that is the constraint. They should all be inside this box. Fine. Let us look at the constraints now. So, the physical constraints say, the first set of constraints they tell you that every pin of the net E must be within the bounding box. These are captured by these 4 constraints. Left E must be less than equal to the x coordinate of the center plus that offset for that pin E, for sub pin E, for every V belonging to this net, this V must be this. Similarly, right one should be greater than or equal to this. So, it should be within that range. Bottom again should be less than or equal to the y values, top should be greater than or equal. That means, this V should be inside that imaginary rectangle. Secondly, the total net length is estimated as the half parameter. You recall, this was one of the measures. This is called half parameter wire length, because it is a rectangle, you take the half parameter. So, length plus width. So, from left right you can say right minus left plus top minus bottom, that will be your half parameter. So, your half parameter can be calculated like this, right minus left plus top minus bottom. So, timing constraints you can similarly add like this. So, some notations, T gate V I V 0 is defined as the gate delay from an input pin V I to the output pin V 0 of a particular cell, and T net E U 0 V 1 is net E's delay of a net from cell U's pin, some output pin U 0, it is coming from a cell U 0 is the output pin and it is going to the input pin of V, it is called V I, that net delay. And AAT you get from static timing analysis, this is the actual arrival time on pin J. So, there are a few timing constraints you can identify. The first one is, you are saying that for every input pin of cell V, the arrival time at V I will be the arrival time at the previous output pin U 0 plus the net delay. So, AAT of V I should be the arrival time in the previous output plus the delay of this net from U 0 to V I. Okay, this is clear. This is one. Similarly, second constraint will be, for every output pin V 0 of a cell, the arrival time at V 0 should be greater than or equal to the arrival time of each of its inputs plus the gate delay. So, for a gate, the arrival time of the output should be greater than or equal to arrival time of the input plus the delay of the gate. Okay. The third constraint concerns the slack. It says that for every pin of a sequential cell tau, let us call it, the slack is computed as the difference between the RAT minus AAT, just the definition. So, slack for every timing point you are calculating as difference between RAT and AAT. So, you see this RAT and AAT calculation, the static timing analysis, they should be available as some kind of function. You will have to get those values whenever required. So, static timing analyzer is available to you, you are assuming that. And of course, the slack values can be upper bounded to 0 because you do not want a positive slack value, because you have seen earlier we use something like 0 slack algorithm, so that we try to bring all slack values close to 0. So, either you just upper bound it to 0 or use a small positive value, so that the slack values all reach close to 0 within that range. So, the objective function can be three types, three of them are shown here, you can add some more. First one is to optimize the total negative slack. Total negative slack can be expressed like this: pins tau is the set of pins of a cell tau and t is the set of all sequential elements or endpoints. So, you calculate the slack of all such thing. One thing is not mentioned, if it is total negative slack, you will also have to mention another condition, that slack tau p should be less than or equal to 0, right. But here, since you are assuming in terms of a constraint that slack tau p will be less than or equal to 0, so it will be either 0 or negative, it can never be positive. Okay. So, under this condition you can assume this, just summation of the slack tau p, this will give you the total negative slack. Then the second condition may be you optimize the worst negative slack, max WNS. Worst negative slack also, you know the expression, you can calculate that. So, WNS will be less than or equal to slack tau p for all tau p, and you can make some weighted combination sum of the total length of the net wires and let us say the worst negative slack WNS. So, you can use this LE as the half perimeter wire length for all the nets sum total, and you can use this WNS negative slack. So, this alpha can be a parameter between 0 and 1. So, using that you can actually control the impact of the area, the length of the net and the slack. So, these are the typical objective functions which are used here. Okay. So, you see here we looked at a few things. We looked at that how we can do placement taking into account the timing characteristic or the timing parameters in mind. You see, earlier when we did placement, we ignored timing, we only looked at the location of the blocks and minimization of the wire lengths. Now, we have an additional parameter that is coming in, we are trying to minimize slack, we are trying to minimize delay and so on. So, you now require or you now have an environment where the placement tool and the timing analysis tool are working hand in hand. So, here we just mentioned a couple of methods, more advanced techniques are also available, but here we have not discussed those. They really work hand in hand and they are capable of handling large designs as well, because you see, because the industrial designs are large, we need to have a method whose time complexity is not large. Of course, we would like to have accuracy, but we would also have to look for scalability. The method should be able to handle larger circuits that are practical in today's scenario and so on and so forth. So, now that we had talked about timing driven placement, there are other issues that we will be looking at later during our next week's lectures, which I will be looking at, for example, timing aware routing, timing driven routing. So, how to make the geometry connections for the nets such that some timing estimates or timing budgets are satisfied. And finally, whenever we have to satisfy some timing budgets which you get from the timing analysis tool, how to make annotations or modifications in our net lists or in our devices such that those timing analysis or the requirements can be met. Okay. So, with this we come to the end of this lecture. Thank you.